Hello class, welcome to Pre-Algebra Lesson 9.5, which is all about scientific notation. By the end of this lesson, you should be able to express numbers in standard form and scientific notation, and you should be able to compare and order numbers written in scientific notation. So let's talk a little bit about what standard form means and what scientific notation means. So standard form is when numbers are written without using exponents. So those are pretty much the numbers that you're accustomed to working with, right? Like 1 is a standard form number. 25 is a standard form number. 1 million is a standard form number because there aren't any exponents, okay? Scientific notation is a faster way to write really, really big or really, really small numbers. So if I wanted to write, let's say we were working with 10 billion, or actually, 10 billion in a problem, that would be really, really annoying to have to keep writing over and over, right? So we use something called scientific notation, where we can write numbers like this. That's a lot faster to write than 10 billion. And as numbers get even bigger, or numbers get even smaller, because it works the other way too. If you were to have lots and lots of zeros after a decimal and then some numbers, you can use scientific notation to write that in a faster manner. Okay, so the form is always the number, which has to be between 1 and it can be 1, but it has to be less than 10. Okay, so I couldn't say 10 times 10 to the 10th. I would have to change that number to be a 1. And I'll show you, what I mean by that on the next couple of slides, okay? So that number out front that you're multiplying by 10 to the something always has to be 1 or greater than or equal to 1 and less than 10. Okay. Then n is an integer. So that means that we're not going to have decimals for our exponents. Those exponents always have to be nice numbers. They have to be integers. Okay, no decimals up there. Okay, so let's practice converting from this scientific notation, to our standard form. So this is my scientific notation. You can see I have a number that's either greater than or equal to 1, but still less than 10. Okay, so 4 meets that requirement. And then my exponent is an integer, right? There's no decimal up there. So what this means is I'm going to take that 4, and there's always an invisible decimal point. If it's not written in, it's always right after your last number. Okay, so I have a decimal point right there. And then just to help me remember I have that decimal point, I'm going to add a 0. So 4.0. Now, this 2, when it is positive, you're going from standard form to scientific notation. When it's positive, you are going to move your decimal place that many units to the right. So this is going to be moved to the right. So I'm going to move it 1, 2 units to the right. And now I have to fill in another 0, so that way it's not just an open space, right? So 4 times 10 to the second power equals 400. And that would be my standard form version of that scientific notation problem. Okay, and before we move on to that second problem there, let's pretend we have 4 times 10 to the negative second power. What happens then? When it's to a negative exponent, you move to the left. So it works the same way. You say 4, okay, there's my decimal point, but now instead of moving 2 to the right, I am going to move 2 to the left. So I move 1, 2. Here's where my new decimal point is. I need a 0 there. And so now I can see that my answer would be 0.04 in standard form. Okay? So that positive and negative exponent just tells you if you're moving your decimal to the left or you're moving it to the right. All right, let's look down below at this next problem. We have 14 times 10 to the negative 6. Right away, I notice that my number out front is not less than 10, right? Because my decimal is right here. I need it to be right there. So this would be 1.4 times 10 to the, since I moved it 1 unit to the left already, it is now to the 5th. Okay, so when you are in that scientific notation and you're moving to the left, okay, it's going to adjust your number. Okay, now we're going to move on from there. I'm going to say 1.4 times 10 to the negative 5th. Here's 1.4. And since I'm going negative, that means I'm going to move it left 5 units. So 1, 2, 3, 4, 5. Okay, so I'm going to put my decimal here. And I'm going to fill in where all of those little things are. Okay, so that means my answer is 0.000014. Okay, and honestly, if you had just done that right off the bat from here, 14, I'm going to move it over, 14, here's my decimal, I could have just moved it 6 to the left. I just wanted to point out that it's important to watch for that number that's bigger than 10. So 1, 2, 3, 4, 5, 6. There would be my new decimal point. And you can see that we end up at the same exact number even when we did it with a negative 6 for this time. Okay? All right. Now let's practice a little bit more. We have 5.69 and it's to the times 10 to the 12th power. Since it's a positive 12, I'm going to move that decimal place 12 units to the right. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there's my new decimal point. So you can see that's a very, very large number that we don't normally work with numbers quite that large, but in this case, we are. Okay, so that would be my answer. I moved my decimal 12 units to the right. All right, now let's look at another example where we have 3.25 times 10 to the negative 5th. So I'm going to say 3.25. Negative means I'm moving to the left, so I'm going to move it 1, 2, 3, 4, 5. Erase my decimal from the starting position, and this would be my answer, 0.00000325. That would be my answer in standard form. Okay. Now let's practice going the other way. All right, so this is a big number, right? It's not a decimal. It's not a little decimal. It's just a big number. It's 7 million. Here's my decimal. I need this decimal to end up right there after my 7. So I need it to say 7.0 or just 7. Both ways are fine. Times 10 to the, and I need to figure out how many positions did I move that decimal point. 1, 2, 3, 4, 5, 6. So it'd be 10 to the 6th power. So both of those are acceptable ways to write the scientific notation. All right. When we are dealing with a number that's a little itty-bitty decimal, you're going to do that same process where you need this decimal to be after, in this case, that 8.27. That number's between 1 and 10. So I'm going to say 8.27 times 10 to the, since it's a decimal, I know that it's going to be a negative. Okay, so I'm going to go 1, 2, 3, 4, 5, 6, 7. So it would be 8.27 to the negative 7th power. All right. Let's practice another one. 18,240,000. I'm going to say 18 to 4. My decimal has to go after that 1. This is where I want my decimal. So I need to figure out, okay, if my decimal's here, how many places am I moving it? I'm moving it 1, 2, 3, 4, 5, 6, 7 places. So I say 10 to the, is this going to be a positive or a negative 7? This should be a positive 7 because we're dealing with a really big number rather than a really little number. Okay, so 1.824 times 10 to the 7th power. Now this time, I'm going to have a 6.7 because I want my decimal to be right after that first non-zero digit. So 6.7 times 10 to the, now I'm working with a decimal number. So that means that, and when I say when I'm working with a decimal number, I should maybe be a little clearer. I mean that my standard form is a decimal. Okay, so that number that I'm starting with is already a decimal. Okay, so 0.000067, I have to move that decimal 1, 2, 3, 4, 5 units. And since it's the decimal number, I know it's going to be a negative 5. Okay. Now let's practice comparing numbers. So we have about 1.372 times 10 to the 7th square kilometers of Antarctica, and we have 1.834 times 10 to the 6th square kilometers in Greenland are covered by an ice cap. Which landmass has a greater area covered by the ice? Okay, so let's figure out, we're going to do it kind of a longer way first, and then we're going to talk about how to identify using a shorter method, okay? So if I were to convert this to standard form, because you're used to comparing numbers in standard form. So 1.372, I need to move that 1, 2, 3, 4, 5, 6, 7. Okay, so here's where my new decimal is. I need to fill in zeros. Okay, so this is how big that ice cap is in Antarctica. So 13,720,000 square kilometers. Let's compare it to the one in Greenland. I have 1.834 times 10 to the 6th. 1, 2, 3, 4, 5, 6. So that means this one in Greenland is 1,834,000 square kilometers. So when it's in standard form, this is what you're used to comparing. You'd easily be able to tell that Antarctica has a bigger ice cap. Okay, so that would be Antarctica. Okay. Now, what if you didn't want to actually convert it to standard form? How do you compare when they're still in scientific notation? Okay, so if you look at these first two numbers, the first thing that you can do to compare if a number's bigger is you look for which one has the bigger exponent. So if you look at Antarctica, it had a 7 for an exponent. That means that it's going to have one more digit than our other problem, or our other number, because our other number only had an exponent of 6. So if they have different exponents, and you're looking for the bigger number, you look at the number that has the bigger exponent. Okay? If you're comparing two really little numbers, you're looking for the number that's either the lesser of two positive numbers, or you're looking at two numbers that are both negative exponents, in which case you want the bigger negative. Well, when I say bigger, that's not the right way. But if we're looking at negative exponents, the further into the negatives you go, the smaller the number is. So like -5 would not be as small as like -20. Okay, so you want to always look at the exponents. If they have the same exact exponent, then you start comparing just the numbers up front. Okay, so if they had the same exponent, you would just compare the two numbers that are being multiplied by 10 to whatever power. All right, so with that information, let's look at this problem. Over the time periods shown in the table from oldest to order the time periods shown in the table from oldest to youngest. Okay, and we're talking about geological time periods. So we have the Jurassic, the Silurian, the Tertiary, and the Triassic. Sorry if I mispronounced any of those. But if we look at these numbers, right off the bat, I want to go from oldest to youngest. So oldest means I'm looking for the biggest number. And I see that I have 3 exponents that have 8. Okay, 3 exponents with an 8. So that means I'm going to compare the 3 numbers being multiplied by 8. And I say, okay, out of those, which is the biggest? That'd be the 4.38. So the oldest would be the Silurian. Then, because that's 4.38, that's the biggest number there. And then I compare 2.08 and 2.45. 2.45 is the next biggest number, so I'm going to say Triassic. After Triassic, I have Jurassic. And then, if you look, the reason I left this one to the end is because it has an exponent that's less than 8, right? It's to the 7th power. So I know right off the bat that the tertiary number isn't as big. So these would be this would be the order for those 4 numbers. All right, if you have any questions at all, please don't hesitate to reach out for some help. I am happy to help you. Have a great day.